So the next idea that we're talking about is how to predict the products of a chemical reaction, where we just tell you what stuff is being mixed together and you get to figure out what are we going to create. And this is really one of the most powerful skills that we can teach you as a high school chemistry student. It's one of the things that y'all want to be able to do. What is this going to make if we mix these things together? Well, this is the start of that skill. This is going to cover all of page 10 and then just the top section of page 11. So let's get to it. The first type of reaction that we're going to be focusing on predicting their products is combustion reactions. And as you can see on these pages, the type of reaction is how we're organizing these skills. And so you really need to be able to recognize your types. And this might actually help you reinforce being able to tell the difference between some of these types. But it's a really important skill to have that's going to help us with what we're doing here. So a combustion reaction, in general, if I tell you something is burning or is on fire, then that's a sign in words that in real life you'd be seeing a combustion reaction happen. And remember, combustion reactions always need oxygen. Fire needs oxygen to burn. It needs to breathe just like we do. And it always makes the same two products, carbon dioxide and water. So because of this, these are the easiest ones to predict, because as soon as I tell you something like methane is burning in the presence of oxygen, then you can write down that reaction. Methane, CH4, is burning. If I've told you burning, you can already figure out everything else. But sometimes we mention in air or in the presence of oxygen to make sure you remember that we're going to have to add O2 there. And then we're going to be producing CO2 and H2O every time. I don't have to tell you that part, because as soon as you know it's combustion, as soon as you know this is burning, then that's going to be the two products, the only possible products. So in this next one, if I say that propane is burning, that's all I tell you. Okay, well, maybe I tell you what propane is because it's a little bit of a weird name, but propane is C3H8. Then all I have to say, propane is burning. Done. Well, in order to burn, what else do we need? Oxygen. And if we know this is burning, this is combustion, then we're making CO2 and H2O. In the lab that we did, you put ethyl alcohol, ethanol, on the lab table and ignited it. That's all I had to tell you. And at this point now, you should be able to say, okay, ethanol was ignited in the presence of oxygen, which means it made CO2 and H2O. So I want you to go ahead and finish this octane example. I want to see a reaction written out, even if it's not perfect. I'll stamp you even as long as it's not blank, but it shouldn't be too hard to finish that one out. Now, if we move on to synthesis reactions, remember, synthesis reactions take separate things coming together to make one product. And while these are not always two separate elements making one ionic product, that's the only situation we are going to give you. Because as a high school chemistry student, you can't necessarily predict the types of covalent compounds that'll happen. Because remember, like hydrogen and carbon can make hundreds of different, if not thousands, of different formulas and combinations in a covalent bond, different ways to share, and different ratios. So as a high school chemistry student, we're only going to ask you to do one specific, simplest type of synthesis reactions, where you have two separate elements coming together to make one ionic product, which means we're going to have to use the charges of those ions to write the formula of that compound. And the other thing that you need to make sure of, other than knowing your charges, and we will tell you, like what we've done here, the charges of some transition metals, if those are going to occur in a reaction, is that we always put the positively charged ion first and then the negatively charged ion. So when you're looking at the elements that are coming together, sometimes, like here, we are giving you the positive one, then the negative one, because magnesium likes to be a +2, oxygen likes to be a -2. So when we put them together to make this product, that's just going to be MgO, because that +2 and -2 cancel out. If somehow, or for whatever reason, we had told you that that was oxygen plus magnesium, then you'd still need to write the final product as MgO, not OMG. The ionic compounds are always positively charged thing, then negatively charged thing. That's really all we got to do is check charges, arrange the elements correctly, then cross drop reduce. So if we look at this next one, lithium has a +1 charge, oxygen has a -2 charge. So we're going to put a lithium and an oxygen together, and when we cross drop reduce, oxygen's -2 charge is going to be crossing over onto the lithium, and lithium's +1 charge isn't really going to be written down because we don't write ones. So that means that we are going to be making Li2O. Now, I just wrote down those charges underneath the separate elements, but that's not really part of this reaction, and it's not really lining up very well. So I guess if I was writing this out, especially if I was going to have to balance this like you will on a test, then I would want that to maybe look like a little more part of that reaction there. Now this next one, notice we have our iron here. If I look at the periodic table, I can't tell what iron's charge is, but we will tell you what the charge it's going to have is in that kind of area, just like what we've done here. So iron likes to have a +3 charge, so we're going to treat it like a +3. Chlorine is a -1, so we're going to put iron before chlorine. And when we cross drop reduce, that 3 from the iron is going to be crossing over onto that chlorine. So I want you to go ahead and finish this last one. We got some simple elements, no weird transition metals. Just check the charges, cross drop reduce to see what compound you're going to make. Once again, as long as it's not blank, I'll give you some stamp on this page, but I need to see you try. Now, top of the next page, all we're going to do is talk about these decomposition reactions, and then we're done with this podcast. And remember, decomposition reactions are the opposite of synthesis. And so we're going to be taking one compound and breaking it down. And much like how in synthesis, we're going to keep it to the simplest case that a high school chemistry student can manage, here, we're only ever going to ask you to decompose a compound all the way down to elements. Remember that A and X could be compounds, technically. We can have a compound breaking down into other compounds, and that is still decomposition, but we're not going to ask you to predict those types of products because that can get really complicated. So if you see one reactant, you know that has to be decomposition. That's the only way you can tell. That's the only thing that can happen to that one compound is it breaks down. And you're going to break it down completely into its elements. So basically, MgO, we're going to be breaking apart the Mg and the O. And the most important thing to remember here is your diatomic elements. Remember Brinkelhoff, or I Bring Clay for Our New House, tells us the 7 elements that have to have a 2 on them when they're separate from all other elements. That's 7 elements that can never be completely alone. So as I'm writing out these 2 separate products, magnesium and oxygen, just separate them. Doesn't even really matter what order they're in. I generally leave them in the order they're written, but then we check our diatomics and realize that oxygen is a diatomic, which means we give it a 2. Same type of thing in this next one. H and Cl are going to be separating from each other, so we're going to be making H and Cl separate. Check our diatomics. Both of them are diatomics, so both of them get 2s. That's the only thing we care about with elements is are they diatomics or not. So this next one, H2O, we're going to bring apart the H and the O. Don't worry about these numbers down here for now. All we care about is taking the elements and separating them, checking if they're diatomics. Yes, they are. So they both get 2s. So do the same thing over here with these last 2 reactions. Try them out. And as long as they're not blank, I will stamp this page for you. And we will pick up with those single replacement reactions that you see at the bottom of the page in class.